Hey everyone, apologies for being late. They got derailed with other conversations. Um, I'm going to try and keep it brief and get us closer to on time. Although Kuba said take as much time, but yeah, yeah. And the goal of this presentation is just to kind of like get you thinking in subnets and get you thinking in just cross chain calling. And so this is kind of late in the IPC track. I think everybody has been looking at a lot of the model and so on already. I just kind of the way I've structured this is to spend a little bit of time thinking about the model and where this came from, then talk about Filecoin regions, and then talk about what needs to be true to make sharding into regions actually practical. Because today, cross-chain calling is a nightmare in most of the blockchain ecosystem. Going back to the model, this is where IPC came from, which is kind of thinking about, it's one of those cases of zooming way out and looking at the blockchain world in context of the longer computing paradigm, or as part of like one computing paradigm embedded in a large series of computing paradigms, realizing that the consensus bottleneck is kind of an accident of history and not something there because of theory, and that it's a bottleneck that will get opened up dramatically, and that if we look at hardware and we look at kind of the 99.99% of computing in the world, this bottleneck should just not exist, and that there's good standard distributed systems ways and techniques to scale out of this bottleneck. Now you could do the scaling in a lot of different ways, but we chose this pathway through trees and scaling chains this way because this is likely an easier to develop and build in the long term, and easier to get adoption in. There are other models that could likely be better. You can think of fully distributed runtimes, like full like Erlang style actor VM type model of the world that could actually work. I think Sui is going in kind of in this direction to some extent, but it's less likely. My view is that it's less likely to get adoption as quickly as something that actually fits with the chain model. But in any case, like the broad motivation is to be able to fit the real scale of computing of the world in chains, meaning we need to be able to deal with large-scale applications doing large-scale application things. So just to put numbers into perspective, like we're talking about, we were doing this exercise together in the Filecoin. So earlier in kind of talking about constraints, like we're really talking about massive scale applications, massive scale operations, billions of people on the planet using devices, 3 billion devices, trillions of requests per day. That's just in HTTP, let alone kind of like all the little RPC calls everywhere happening. Quadrillions of data objects, all mutable, and so on. Zettabytes of storage and so on. So you can think of massive scale applications, and that the throughput's required to be able to build something serious. If you want to build a social network in crypto or whatever, or in Web3, you're going to be hitting these numbers pretty fast. So we step back and realize that we needed something kind of in this target, and so we've been developing towards this. And one embedded piece of the picture is to kind of think of a lot of different computational paradigms and different calling conventions between them. So think of the world of the cloud virtualization and the hypervisor model, or containers, or even kind of like the Cloudflare workers, Lambda style, Amazon Lambda style thing. All of these different computational models evolved along the way to kind of take advantage of different efficiencies of scale, or different types of hardware, or different types of utilizing the same hardware to serve more use cases. At the end of the day, it's all about how do you describe the computation that's going to run? How do you do the correct message passing between the requester and the processor and so on? How do you pass access control capabilities and things like that? How do you schedule the computation? How do you move into the right place and so on? So similar kind of problems in this scale. So the kind of core insight here is to say, if you really want to fit massive scale applications in this high security model, you need to do it with sharding of some sort. You don't have to use a tree. You could have some kind of very I think some people might propose a way to do it without trees that might be more like transactions between every single subnet and whatnot. Those tend to be harder to reason about and harder to develop. And so trees tend to make things easier to reason about, and security flows in one direction, which is much easier to kind of model and make part of transactions. But at the end of the day, what you want is an environment where you can, over time, as the demand for computation increases, just fan out into smaller and smaller and smaller subnets. And one other characteristic here is that these subnets, you can impose restrictions for these subnets, like geolocate them in a specific region of the world. And that's a key characteristic here, because today blockchains are rate limited by two things: block space and kind of the validation time that it requires to validate a single block, and the speed of light in the propagation delay of a block going through. So you can really start looking at doing high throughput applications and doing lots of things if you solve both of those problems. The first one you can solve with fan out. You have more subnets, and so the validation time per chain decreases. The second one you can solve by having subnets that are restricted in space. So you can think of the extreme case, which is kind of a single computer. That's like just a normal sequencer in other L2 type strategies. A single computer could be running a bunch of operations, and that's, you don't have to worry, like the speed of light distance between, the CPU and RAM is like a really great place to be. In other computational models, you might end up having multiple nodes there, but you can constrain the space of these so that you can move the block times extremely quickly. And so you can have a chain with something like 10 millisecond block times, and like that could actually be realistic, or 100 millisecond block times or something like that, by bounding the set of nodes that are able to operate in that shard. So one other thing I'll mention, or one claim about computing history in general, is that just virtualization and layering and so on will come along the way. The thing that's really important in all of this is the applications and the calling convention of them, and being able to kind of have a very smooth and portable environment that tries to limit how much information from the rest of the world is entering the application. So having a really nice environment where applications can move and be portable will be a key property that blockchains will emerge, or will finally get to. So when we're kind of like looking at this problem, we saw there was going to be need for a hypervisor VM of some sort, and we're going to need some kind of distributed runtime that allows calling in the kind of Erlang style. And this, sort of translated into two projects. One was FVM to kind of create the hypervisor to enable like lots of different things on top that has shipped, which is really, really great, and kind of live on Filecoin and so on, usable in a bunch of other chains too. We've already hearing from other chains wanting to use FVM as their hypervisor for adding EVM support and other things. And then the other part is IPC to kind of enable and create like that distributed runtime environment. Now, but a key characteristic here is that calling across these has to be easy. We're going to return to that later. Cool. So that's kind of the model of the world. Now, let's talk about Filecoin for a moment and kind of how can we use IPC to scale Filecoin. These are the targets that we want to hit, and there's no way that we're ever going to hit this without scaling of some sort, like I mentioned. And so you can use the IPC structure to then generate regions for Filecoin, and kind of like why Y regions. Oh, sorry. Let me back up for a moment. You get these things from IPC, which is every single subnet is a full chain. It has data availability baked in. So that's one of the properties. That's one of the things that sets IPC apart from just normal, sequencers in other scaling solutions. You have data availability baked into the protocol. If you can create regions that are geolocated, then you can be available through partitions, which is required by a lot of the applications that we're talking about. You're just not going to get a social network that is going to fall apart because connectivity sort of broke. Some internet hiccup happened, and then connectivity sort of broke. The real world applications have to work through these kinds of problems. Any kind of major city goes through kind of outages in some cases and or congestion, and you don't want that to inhibit the operation inside. And then IPC gives you this kind of scaling in two factors. One is kind of you can scale vertically by kind of creating more subnets, or you can scale horizontally, which just means adding kind of parallel trees, right? So you can kind of scale down one level and kind of create a bunch of subnets there. And as demand in different regions emerges, you can kind of go deeper into each one of these. And you can pick the structure of the tree well so that you can have really fast block times in some of these. And know that requires, like the fan out here gives you these two nice properties. One is you can distribute a lot of the computation down into more space. And second, you can accelerate the block time. And so you can, today kind of like the woes of the L1, supersaturated L1 are gonna go away. Or rather, the L1s are likely going to be continue saturated, but a lot of the computation is just going to move down and fan out down into the subnets. So yeah, we can use IPC to give Filecoin regions. I'm going to use two terms here from the normal cloud computing world, the word region and the word zone. And the kind of definition of these is that a region tends to map to a specific data center. A zone is kind of like an availability zone. And usually in a lot of data centers, the expectation is that zones might be in the same physical location, the same physical data center, but they need independent power, independent internet access, and so on. And so zones kind of give you kind of an additional notion of availability within the same physical location. In kind of like real world cloud systems, this kind of stuff matters, right? Like we're talking about like, not only have you split up your massive scale deployment into, somewhere between 10 and 30 data centers in the world, you now even have to shard your data centers because like customers really care about independence from certain kinds of failures that might bring down your entire data center. So let's kind of work through an example. So imagine that you have like the Filecoin's L1 for Earth. Let's call that mainnet. You can start off by creating like two L2s, one in Asia and one in North America. You can think of those as mapping to the continent. You can then create kind of L3s below. And by the way, here, you may not need this L2, L3 layering, but I'm putting in place just to kind of illustrate the concept of the hierarchy. You can then go down into kind of a specific region, what would be traditionally a normal cloud region. So you can, a really easy thing to do would be to look at the current map of regions for the top cloud providers. So Amazon, Google, Azure, Ali Cloud, and whoever else, and just kind of look at where there's kind of high intersection between them, and look at that as a good starting point for what kind of regions should exist. We can lazy load all of these regions and just kind of create a structure and environment where new regions can be added as demand emerges. The continents one, though does not exist in the normal cloud world, might be beneficial for partition tolerance. But it arguably may not need to exist. You can of course keep adding other regions. You can even go down to create availability zones by kind of creating like the different splits, right? So you could go the normal easy route of like US East and US West, which is common in the cloud, or you can use a specific data center location or whatever. You can even implement availability zones as just different subnets. Now, a key property in making all of this work is that calling across of these has to be smooth and easy, so that you can build applications that, if you have, say, storage providers onboarding storage in some region, you want to both like track that. You want to enable that onboarding to happen in that region, but you want to enable transacting across regions. Now, there's going to be some time costs associated with that in terms of the latency of some process going from one subnet to another subnet. But it should be easy from a programming perspective. Like this, it should not be kind of prohibitively complicated and annoying to call across these regions. If it is prohibitively annoying, it won't happen, right? Like the developers won't stand for something that is extremely, extremely complex. Cool. Any questions so far? Yeah.
Hey, I was wondering if this separate subnets that kind of correspond to each region or subregion can have different block size, like.
Yeah, totally.
Like
they could have different block size.
Does it have to be like? Can it be less than 32 gigabytes, which is kind of sometimes is it sector size? So sorry for terminology.
Sector size is an independent question. Sector size is more about the proof construction. So unfortunately, right now, the sector size gets attributed to Filecoin, as opposed to, in reality, the sector size is attributed to the proof structure and the smart contracts that today interact with that proof structure. So for example, the miner actor today and the storage market today and the current proof characteristics, like all of those together define that particular sector size. Coming up with a new POREP and then creating smart contract or evolving the smart contracts to deal with that new POREP would solve that problem. The future likely has many POREPs tuned for different hardware characteristics. It's a whole separate conversation, but today we're using a POREP that requires hard drives and turning hard drives into tape. And it'd be really, really great to have a POREP that takes hard drives and gives you hard drives, as opposed to creating tape out of hard drives. Bonus points if you find a POREP that takes a hard drive and gives you flash, but we'll leave that for a species smarter than us. Cool. So any other questions about that kind of stuff? Block times can be very different here too, right? So you could have a region that moves super quickly. Ideally, we should always be rate limited. The block time should always be rate limited by propagation time, not by validation time. So today, most chains are rate limited by validation time because people are trying to fit a ton of computation into them, right? Ideally, the fan-out structure would be primarily rate limiting by the propagation delay of information going through. And the moment that you're starting to see that the validation time creeps up on the propagation delay, you should just shard. You should either horizontally scale or vertically scale. Because that's how you can keep things moving, right? So I'm going to make a controversial claim. We plan to have, as a demo, an FPS running on this, where your movement as a player is verified by a chain. That should be possible. It just kind of seems kind of crazy, but that's kind of this is the speed that we're going for.
So just to confirm, I think you might have just done that actually in the last couple of sentences, but this is just to do with literally the speed of light. I mean, that is why we're going down the geographic separations of this. This is why, we're just, the laws of physics are what are constraining us here.
Correct.
Are there any other reasons for the regional or any other benefits of the regional breakdowns?
Yeah, so there are other benefits, like the regions give you jurisdictional separation, where there might need to be subnets that follow a different set of rules because of different jurisdictions. That's entirely possible. We'll see that develop in the blockchain world. There might be application-specific splits. So this is a strategy presenting sharding across, just based on geography and treating all applications the same. There might be a different way to shard, which is kind of applications themselves choosing their own sharding structure, tuning for an application, right? And so you might have a whole other parallel tree here that is for a specific application, and calling between those should be easy. Like if we can make it really easy to call between these, as easy as two processes, two HTTP processes talking to each other in a normal calling convention, a lot of this stuff is going to become super easy. But we have to get the calling convention right. Other questions? Yeah, back there.
There's a microphone on the table right there.
Hey, so question is like you need regions for data, right? And maybe it's a little bit stupid question, but like this is IPC subnets. These are about FVM and nodes who run FVM, right? On subnet. But for data and for like GDPR rules and all of these regulations, it's important where the data is located. So it should be like data providers, the nodes who like store data, should be also in this region, in this location. Like how these nodes map to like actually storage providers.
So right now the parties that run the consensus, let's just call them consensus providers. They might just be the storage providers, or there might be some other role. Leave that aside for a second. In this case, like you would map a storage provider to a specific region and onboard their storage to that region.
It might be also infeasible for you to have storage in another region and still prove this storage in given region.
Yeah. So this doesn't yet talk about the concept of proof of location, but a proof of location is a way of you use a network of nodes to establish a strong cryptographic or economic claim about the actual physical location of a device. Based on things like latencies, based on things like, there are some that do like trusted hardware things and so on, but you can use latencies for this. And so proof of locations, you can use the proof of location network to establish the location of something. It would be great to evolve the storage proofs so that you could actually get strong guarantees about the location, the physical location of the data. But that's kind of like a whole separate conversation.
Okay.
Are zones going to have consensus between them?
Yeah. So each one of these is a full blockchain. Oh, so the checkpointing up. So a subnet. This is kind of what the IPC framework gives you. IPC gives you a framework to create the relationship between a parent chain and a child chain, such that the child can checkpoint into the parent, and the child is able to derive security from the parent by checkpointing. So when the child checkpoints into the parent, then that state is now secured by the parent.
How much of this information is going to go up to mainnet?
Just the checkpoints.
Just the checkpoints. Okay.
Yeah. Plus, I think like there's some amount of one of the message passing structures goes up to the parent, right?
Yeah. So we pass the set of bottom-up messages and the state summary, so the state hash, which is the checkpoint.
Do we still do if you call from a sibling to a sibling, do you still like route through the parent?
Yes. So right now we have been discussing using ZK constructions to just provide a proof to basically bypass that and then still propagate, because we need to update all the balances hierarchically, but we would have a fast path, a fast shortcut.
Yeah. And also there's all kinds of good optimizations there, but like the basic model is like when you do one way of doing it is like when you call from one sibling to another sibling, it kind of goes to the parent. Depending on the speeds there, that can be the sort of thing that gets things to be abysmally bad for developers. And so that's where what George just said about ZK constructions ends up being really valuable, because then you can kind of really just do a call from one node to another node. You should be able to do like two-phase commit type things too. But anyway. Other questions? Yeah, back there.
Hey, this feels, I don't know, like a pretty normal, semi-obvious question, but like, why do I use this over, the previous question had like avalanche subnets and how they've grown. Why do I use this over another L2 or another sequencer?
That's a larger question. The way that I would answer that question is more about like IPC runtime specifics. So I would there are like Filecoin specific answers. For example, in this case, we're talking about data that's on Filecoin or computation that's on Filecoin and so on. So you're already in the Filecoin world and you want to use scalability here. Like you cannot use avalanche subnets, period.
Got it. But like, can I still access the data on the main chain if I'm, posting those state routes from the, the different subnets?
Yes, correct. Yeah.
Got it.
The separate question of kind of like independent of Filecoin, why you would use this, the computational paradigm, we think is going to be better. But that's a whole separate. I'm going to leave that unanswered, or I'll claim that, and happy to talk about it at a future point. And one important thing is like subnets don't have to be a large consensus of nodes. You can create a construction that has a single node, but you need parties need to know that that's like what they're signing up for, right? So if you squint at it, then traditional ZK rollups are very similar to this. And I don't know if this is implemented already, I know this is not implemented already. I don't know if it's roadmapped. We want to have kind of ZK style proofs as well. Like, so you could have a subtree that's just ZK nodes. And so you could have an entire subtree of ZK nodes. But it's still kind of fitting within the same calling convention, because one of the things that has been true about the world of computing is like you have to get the cross calling between these things to be really good and really easy and really portable. And if you can do that once really well, then the rest can be kind of very smooth. And for this, I think this is where like we should be looking very closely at like all of the different calling conventions that are emerging around the environment. Because there might be one that's already like extremely good that we should just fit. We might need another one. Yeah.
Does the whole tree under a subnet need to be ZK? Because like you could have ZK and then after that you could under that, and there are reasons to have that because you might have other ZK. But like under the same subnet, you might want to have like non-ZK subnets.
Yeah. So you're saying if you have a subtree that at some point has a node that is checkpointing with ZK into the top, should you enforce the restriction that all sub nodes should be ZK? Probably. That seems like an easy thing. I don't think you have to.
Yeah, like because you said like everything under that tree is ZK.
Oh, I'm not saying that everything has to be. I'm just saying you should be able to replace the kind of consensus benefits you get from running different parties with stake into a ZK oriented thing. Yeah. Yeah.
I have one question. It's pretty cool, the ability to have like private versus public subnets, but what are the restrictions, let's say if I'm in North America and it's private, but I want to have a zone that is public, or the other way around?
I would think of all of these as public. What you mentioned is also a really neat property from IPC, which is that you can have entire subtrees that are private. Just to spell it out for everybody else, like you can derive subnets that are run in a private regime that don't output information that they don't want to output, and the only output information that transacts with the rest of the tree or something like that. You can have that environment. But yeah, I'm envisioning all of these as public networks that anyone can join. But then the private applications kind of would be separate.
Could be like one private within, let's say, US West wants to be private, even if North America is public. Yeah.
Yeah, you could totally do that. Yeah.
Just another layer of subnets.
Okay. This could be very interesting for industrial reasons or to onboard more enterprise.
Exactly.
Yeah, it's super cool.
By the way, can anyone spot how you make Filecoin interplanetary?
At all 0.
Yes. It's almost like we planned it. Yeah, other questions about this model? Yeah.
Let me just. There's one question.
Does this approach easily support scaling down as well?
It's a great question. Yeah, we've talked about we want to create. Part of the IPC goal is to make generating, running, and removing, like deleting subnets, programmatically very easy, to the point where you should be able to like fan out some computation, run it, and then like destroy it. The subnets here that I'm proposing these ones are kind of meant to be more long running because they kind of mirror the cloud. And so if we assume kind of some success, then we should be expecting these to grow. But yeah, like you could totally imagine a whole tons of other subnets emerging, running some computation, and then removing. By the way, this is kind of how you get like a very cheap compute over data type of network. Like you just put it on consensus and you just run it. Yeah. And the key property of like why that, I think in a lot of those cases, like you have to reason about when you're moving state down a subnet, what is the security level for that application, and then what are you willing to deal with. Cool. Let's maybe move on for a moment. Yeah, so what are subnets good for? Scaling the core protocol, building scalable feature sets, building components as L2s. You can think of, entire applications can be there on subnet trees. There's an open question, for example, like should Saturn build its own tree, or should Filecoin build a tree for a bunch of applications, and then Saturn just runs its own pieces in each of those subnets? This interesting question for us to figure out. But yeah, storage and data.
L2s, when you say L2s here, are they L2s to the L3s of this tree, or?
Yeah, certainly we should have an easy, like a naming convention that makes it easy to localize the object, right? Yeah. Because right now L2 is kind of like this weird loaded term, which just means like it's an L2 relative to an L1, but there's how far does the tree go?
So when you say L2 here, is it first non-Filecoin leaf?
Yeah, so Saturn specifically, so speaking about Saturn specifically, Saturn is going to need at least L2s because of region requirements, maybe L3s, but at least L2s. Yeah. Data onboarding likely needs L2s, maybe L3s. It sort of depends on what the hierarchy is, right? Here I'm introducing the continent thing that is not in the cloud. The cloud has regions and availability zones. We need a mainnet. And then I just threw in the continent thing to just kind of make it easier to think about and think about like deeper trees. Because for example, if like calling from one, you might need that continent one if you have a lot of throughput between like two L3s or something like that, and you don't want it to go through the L1. But I kind of like submit that the continent one could be scrapped if we don't want it.
But my question, if you stay on the slide, so Saturn would be inside L3 US East, or it will be L4 based on L3 US?
No, so I think that Saturn would have some parts of itself in the L1 to register itself as an application that you can transact with and interact with. And then it would have parts of itself in the L3s and parts of itself maybe in the L4s, but probably primarily just needs the L3s here. Because for the Saturn use case, like being in the same city is good enough for CDN. For the CDN problem, for the most part, being in the same city is like sufficient. You don't have to go much closer. Cool. So you get a subnet, and you get a subnet, and you get a subnet. Cool. So all right, like the hard part. So this is kind of like the model that we're going for. What really matters is like cross-chain calling becomes really, really easy. This is why Filecoin actors are called actors. It's because calling across all these different networks is going to need a reasonable kind of computational model to be able to do this. Blockchains today are kind of like in this weird computational paradigm where they're partly message oriented and partly synchronous calling convention. Like certainly smart contracts do synchronous calls within the same VM, but then outside of that, they're just messages. And that's because within the VM you kind of want to optimize and you don't want to do like whole message passing and so on and like the madness that it does to your programming if you try to do that. But you get a really beautiful scaling model if you adopt the messaging constraint. And so the question is like, can we make the paradigms easy to reason about with programming languages? And this is where I think we need to level up our current structure. The Agoric community, which is not just the current Agoric chain, but the team of humans going way back to like, I think it's digital communities or something like that, electronic communities, have been developing the tooling and frameworks for reasoning about this large-scale distributed computation model for a very long time. And what they've arrived at is like this really nice environment where you can just program synchronous code as you would normally in any modern programming language. And then they use the programming language as you would in any modern programming language to do the hard asynchrony parts, right? So imagine being able to program smart contracts with the nice standard async type features, and then have that compiled out to the things that the VM needs to run. So we kind of like should solve the madness of the calling convention in the programming language, not in the things that people are dealing with, right? So today, calling across systems in most blockchains is a horrible nightmare. And it's because we're telling people to like deal with event loops by hand and then to stake a lot of money on it. And people get it wrong all the time. And so we should really just let the computers be good at what computers are and just have some kind of programming language model for it. And so that's something that we do not yet currently have in FEM. And that's something that we need to level up into. So we need to figure out how, if at all, does the FEM need to change itself? And how do we program the FEM to take advantage of calling conventions that are easy? And I think this is where like a lot of the Filecoin application questions can be extremely, extremely good filters for things that are going to be good or not, right? We need to develop a computational paradigm that makes like the hard smart contracts work that like Kuba and A-North and others do feel like better than the current model. Because you don't want to go into like a distributed model that makes it like a lot worse. And so that's where we have a lot of work to do, figuring out exactly how to like construct the interfaces so that writing the smart contracts becomes like hopefully much more intuitive to the developer, and then the computer can do like the hard parts of like how does this get compiled out into like the event loop type model. Cool. Actually, any questions there for the people that do a lot of this programming in the current, programming blockchains right now is like hard in the way that programming distributed systems was before like the modern cloud. When we talk about all of this, I'm sure that like this brings up like lots of concern in your mind of like, like dealing with like storage, like the miner actor dealing with like stuff across all these chains, or like deals, like where do deals go? Like if you have storage in one subnet, what does that mean for deals in another place? Like, does that mean that you must hire them there? Like, yeah, so those are the kinds of questions that we need to translate into requirements that then become requirements that the software has to satisfy to then make it like easy to deal with. And so something that I think would be maybe very useful in like Kuba's section is to kind of like reason about what do you want to make possible out of this runtime, or kind of like what are your baseline requirements that this technology set has to meet in order for you to be like, oh yes, awesome. Yeah. Like,
it's sort
Yeah.
the parent chain, but we'll have the whole snapshot. Does the chain just have to maintain that to bootstrap new members of the subnet?
It's all IPLD. It's all IPLD data, right? So what we can just like store it in Filecoin.
Okay, so but
Yeah.
so that would mean
So yeah, and like we talked about this earlier, and I think it's a great point to make. I don't know if you talked about it earlier today. So Andrew was talking about like this really important concept here, which is like you need to make booting up a subnet, running it, and then suspending it super, super easy. And so like rehydrate, like the concept of rehydrating a thing in computer science, it's like taking some stored compressed state, booting it up into a running system, and then kind of suspending it again. That needs to be easy. And we can do that because like all of the chain is IPLD data structures. So we can just take the entire thing and store it in the parent, or store it further up, or in whatever their storage. So what is not pictured here is the storage providers, which are a different set of nodes that are available to store your data. We would want the state of the chain itself to be poured in. And so think of snapshots as like you could take like at some point you accumulate enough state and you then like put it into a deal and you store it.
Yeah. So that is kind of part of what we're trying to tackle. But the like movement of the data from the subchain to the storage provider is like a third connection in this tree.
Yep. Yes.
The whole state doesn't
Yes.
move over a transaction to the parent. And so I was just curious if there's like a long-term.
Yeah, the currently not pictured is like how you would call out to those storage providers or whatever. Yeah. You can just imagine a set of storage providers that exist on the side that you're then hiring to store your data.
Also, if you have a storage provider in a subnet with yourself, right? If the storage provider is one of the validators of that subnet, they possess all the state.
I would just really like create a very hard abstraction boundary here and say that like IPC subnets can hire the Filecoin storage providers to store their state, but that should just be a CID, right? Like it should just be, I'm trying to boot up this subnet, I have this CID, and I want a snapshot that is gonna let me boot this up.
Yeah, so that's where it kind of gets back to your programming language and abstracting that out to make it easy, because in my mind, it's like you checkpoint, and at that moment of the checkpoint is when you kind of want to guarantee that, okay, if that subnet went away, at that checkpoint, somebody could come along and reboot this subnet and get it again. But that means, back to the async example, that means that moment that I send just the hash of the transaction, I should also be assuming that it's stored on the SP with, POREP already available and everything, but there's a ton of async then baked into my checkpoint moment that I'm not sure how to see from here to there yet.
The world is very async.
Yeah.
So, I mean, how does the cloud do it today?
Magic to me.
So the cloud today, depending on which cloud and so on, will, depending on the process and how long running it is. I don't know do you ever like notice that S3 for a while would take like 300 milliseconds to load an object, and then after that it was like pretty fast. Yeah. Sorry, not S3, EC2. Yeah. EC2 would like take 300 milliseconds and then would like run. What was happening there is like the VM was being booted up. Like the VM was being pulled out of storage, was booted up, scheduled into a computer, and then run, and then suspended again. And so like the current cloud does all of this. Like they just kind of abstract it out so that like when the request is coming in, the VM itself gets like unsuspended, scheduled, run, and then resuspended. Actually, the resuspension happens if there's no activity, if there's no I/O. So we kind of have to do something kind of similar where like, for some applications in the tree, some subnets should be able to do that. I don't think that the subnets that I was describing earlier, like the main region ones, the region ones are kind of like long running. These ones that we're talking about are kind of like application-specific subnets that should be able to kind of boot up quickly and then go away quickly. But yeah, to your point, like that's a great requirement together of like, hey, it should be easy to boot up all of these chains by a CID, and it should be easy to just store all of that on Filecoin as deals and so on.
But maybe there's also another piece here, which is like that checkpoint, when it lands on the parent chain has the 7-hour finality. So by the time that checkpoint is considered valid, the storage of that state should also be proven in POREP and available so that you could...
So you're talking about like a much harder requirement where it's like, if you checkpoint something into the parent, you should also make all of the state long-term available.
If that is the guarantee of the subnet, yeah.
Yeah, we don't currently have that. So that's a neat addition. I think like some applications won't need it, but I think it would be pretty neat for the main Filecoin tree and the applications that wanted to have that requirement. Yeah. Also good for Filecoin, for all IPC applications and so on to get automatic state storing in here. Other questions? I want to give the time to you. So. Maybe a question for like Kuban and others. Like, what seems like horribly hard here that we should be very worried about to make really good for you?
One thing is what feeds the mainnet consensus? Because if we start moving SPs into subnets, unless we...
The power. You're saying like what is the power notion in the...
in the mainnet, right? Because if we move storage operations, and like a lot of what I was I'm going to talk about it is like a large chunk is this, right? If we move storage operations down into subnets, then either we have to create much stronger guarantees like zero knowledge proofs and so on, guarantees around storage operations, or the power in mainnet has to be fed by something completely different, like pure proof of stake or something like that.
Yeah, it's a good question. So we should evaluate those options and figure out which one we should do. One neat thing here is that once the checkpoint happens into the parent, that's as if that has happened in the parent, right? In terms of the transactions happening.
Collusion thresholds are much lower in subnets, right? If we shard the if we start sharding into subnets, then like...
Yeah, but only one of them will win to insert the checkpoint.
What I mean by that is if the power is recursive, essentially, right?
Yes.
If it feeds recursively, the mainnet is as safe as the weakest subnet.
No. So let's maybe like define our terms more concretely. So suppose that there's still one power table in Filecoin, and then that power table. Suppose that let's just say for convenience that we're going to add them in the blue layer here, right? We're not going to go all the way down. We're going to add all storage power in the blue layer.
Then as weak as smallest blue layer subnet.
No, so once a storage provider comes online and tries to onboard storage and so on, they're doing it in a period of time in that subnet extending. At some point, that subnet will checkpoint into the parent. You can then just enforce a restriction that the power only counts after it's been like sunk deeply into the L1. So that you don't worry about collusion. Like you can the breaking the consensus in a child only breaks between the last checkpoint and the head. That's the beauty of this model. Like what's really cool about this is that like the security guarantees here are that it has to like once something is checkpointed, it inherits the security of the parent.
That's only true if the parent is validating some property of the child.
Yes, correct.
Yeah, and if we offload all storage operations into this, like majority of the storage operations into the subnet, including onboarding, right? Then parent is not validating it without zero knowledge proofs.
Unless exactly. So that sounds like a great requirement to place. So for storage power to be able to be onboarded in any subnet except the L1, we need to have strong validation guarantees because the power really matters to the network.
You can also sample proofs. So in this case, like you can sample proofs and literally slash the entire subnet if they lie.
You could, but I would try to keep the abstraction boundaries between IPC and Filecoin very cleanly separate so that we don't entangle the code bases too much. And I think if we've kind of like so far created a structure where there's kind of like a power table, and you can feed that power table with anything you want on the other side, which could be storage, could be something else. Steven, I think what you're saying is putting into those terms might mean there might need to be a generic way to like challenge power or like ask the power to be verified.
Yeah, but I guess my point here is like you don't actually have to encode this in the root Filecoin rules. Instead, this can actually be encoded in like the IPC subnet smart contract, the one that's managing the subnet, where effectively that smart contract can have some way to dispute any proof that happens to happen on the subnet, and basically effectively just prove that hey, like this snark was wrong or something like that, or like this proof that was accepted by the subnet is not correct. I don't know if that's sufficient though. You might need to fully prove state transitions.
You would need fully auditable execution of the subnet, which is hard.
Well, I thought Stephen's idea of like being able, like if a subnet tries to checkpoint something into a parent, which doesn't pass the parent's audit guarantees, or like it audits the checkpoint in some manner and identifies it as being flawed or malicious, and then slashes the child, that seems like a really interesting mechanism to have in IPC in general, which Filecoin could use in this context for increasing the trust of operations done in that
so you're
subnet.
saying some applications like Filecoin might like the ability to enforce some additional function to be checked in between checkpoints.
But I also want to point out.
I meant literally in the when that checkpoint is checkpointed as a parent.
The checkpoint process itself should allow an application might want to add a function to that checkpointing process.
And then slash the child if it doesn't work.
Bad child.
I want to I do want to point out, Kuba's point here is that like the general solution to this is just to snark the entire state transition.
Yes.
There may not exist any other solution. So like we'd have to very carefully like if you
Like the other solution is fraud proofs, which is
I really
hard.
like full verifiability of the entire tree. I think it's a neat property, or like of a lot of the tree. I think it's a great neat property. Could totally do that.
Zero knowledge proofs is extension of full verifiability, really, right? Because you only not only have the constraint of zero knowledge proofs, but full verifiability due to zero knowledge proofs, but you also have the constraint of zero knowledge proofs, right? Does that make sense? Sorry.
No.
So to have a zero knowledge VM, it already needs to be fully verifiable.
Yeah. So,
So
we
zero
could
knowledge
ask
stricter.
that like the first whatever the main Filecoin regions are. Need to be ZK verified, like all state transitions ZK verified.
So like there's an alternative also, which is two things next to each other, which is you have zero knowledge verifiability for everything that affects consensus power.
Neat. So you're saying like a VM that has some ZK verified state transitions and some not?
Yes. So and they have to be quite clearly separated.
Yeah.
Such that like it's essentially like almost two subnets running next to each other.
Yeah.
But like one of them is purely zero knowledge verifiable, and everything that can affect storage power goes through that.
Yeah.
And then you have normal VM that's way
it's a really
faster,
good idea.
way easier to operate, way easier to write code for, and so on.
That's
way
a really good
cheaper to
idea.
run. If someone has any ideas why this is broken, let me know.
I just think it's like it'll be tricky to weave two different, because you're not talking about like part of the state in a single state tree is going to be ZK verified and part of it won't be, and so the guarantees that you have out of one root is now different, and so part of the tree is going to be ZK verified. You have to figure out a way of like decorating the tree to tell you which parts are ZK verified, and then as you graft the sub trees together into like the mega tree.
So you can abstract it away if you make the so essentially you have L2, which is zero knowledge verifiable, and then L3 is pure IPC non-zero knowledge. So then you have zero knowledge verifiable layer that does storage and does single IPC subnet, and the subnet under that is
I don't know what you mean by pure IPC, but the IPC model is just
no. Like I mean,
structure.
not pure by pure IPC. Sorry, I meant
you mean
without zero knowledge.
Consensus verified.
Yeah, consensus verified subnet under that, right?
Yeah.
So essentially, you're separating instead of having two things next to each other. There are hierarchy, but essentially what the zero knowledge has to do is consensus power and subnet.
By the way, you should take over whenever you want. So like I'm way over time.
We can continue. We can continue.
Are you sure? Because like you have some stuff.
I have some slides. Yeah.
Cool. All right. Thank you.